Hey everybody, my name is Matt Basin, I'm co-founder of Third Wave. We're going to ask me to do the extraordinarily difficult task of introducing someone who literally does not need an introduction for this room. Melonee is one of the most influential roboticists of the last 10 or 15 years, in my view. She was employee number 2, engineer number 1 at Willow Garage, which you've all heard. The internship program that she started there was a springboard for a number of careers, including my own. A number of companies since then, most recently Fetch, was recently sold to ICRA Technologies, and just 2-3 weeks ago, she won the Engelberger Award for being extraordinary. How that goes, as far as I can tell. So without further ado, I'll stop talking.
Awesome. Well, in case you guys don't know that much about me, although Mac did a good job, so I came out to California in 2007. And I ended up stumbling into a whole bunch of luck, and I ended up becoming the second employee of Willow Garage, where I went and spent about a decade being a core developer for Ross and doing a whole bunch of things. But a lot of the stuff that I did at Willow Garage was esoteric research. And what I mean by that is that my grandmother could potentially watch a video I made of a robot taking 45 minutes to get a beer at 8x speed. She couldn't go and buy this thing. She couldn't do anything with it other than look at it and be like, oh, that's cute, Melonee. And although that's exciting at times, you don't want the summary of your life's work to be, oh, that's cute. And so it's one of the reasons I left doing research and went into industry, because I was tired of making videos and building things that only my friends understood and knew much about. And this isn't to denigrate research, it's just what I wanted out of my life. Now, one of the challenges is I decided to go do something like mobile robotics. The thing that we have been proclaiming for the last 20 years almost is solved. I mean, how many people in this room have master's or PhD theses in SLAM, localization, mapping, navigation? Probably half the room. And we have all been proclaiming it's solved, but I can tell you, as someone who's been in the industry and building this, it's a lot more complicated and nuanced than solved. And I would say that much of it is not solved. And why is that? It's because we have an alignment problem. In research, we're trying to solve interesting problems, but they're typically not considered considering scale or safety, and definitely not user experience. There typically are cost constraints. There's no hardware iteration constraints. Build it, rebuild it, throw it out. When the next grad student comes in, he decides he's going to rebuild it, or she decides she's going to rebuild it. Why? Because there's no CPU constraints, and there's definitely no consideration for reliability or uptime. However, in industry, we're building a product. And we have to engineer to the scale that the product needs. We have to provide a basis for safety, because that's what we need to put it into the market in general. You can't sell a product without considering regulations and safety. Those things are inherently important to building products and transferring research into industry. And we also have to provide a usable product. No one's going to buy it if they can't use it. And then the other thing is that we're burdened by other things that suck. Cost constraints, margin. No one's going to invest in your company if you give your product away. And the other thing is that hardware iteration takes time, and it has a lot of downstream effects, like reliability, like CPU constraints, other operational constraints that we typically don't discuss in our research. Like, oh, the robot needs to run for 16 hours. Who has done much of that research? How do we think about that research? We don't, because it's not interesting or novel. It's considered an exercise for the user, the engineer. But the problem is that these are very, very difficult problems, and we could write research papers on them. And in fact, we have, and we've submitted them to prestigious conferences like this, and our work has been rejected time and time again, because it's not considered research. And so I want to put that on the table for you as we discuss this topic and think about these challenges when we talk about the difference of transitioning research to industry. The other thing is that when you look at it, when you look at the the state of the art in open source and the thing that we've been calling solve, when you actually take it to scale, so this is the same map data from the same sensors being played back into what is considered the state of the art in open source was considered what Fetch made for our mapping set. Now, if you look at this building, it's a 600,000 square foot building. And if you were to take data from many buildings that we have, so over the course of the last 7 years at our company, we've probably been into close to 500 or 600 buildings. And the open source stack fails on 90% of them, but it's considered state of the art. And I think it's important to recognize this fact because the problem is it probably is state of the art for the scale that we've been doing research at. We've been doing research inside of our labs, inside of our research facilities that don't get to 600,000 square feet. We never saw a data set that got to 600,000 square feet. And so these are the challenges when you talk about moving something from research to industry is we have a lack of depth in our data to even understand whether the research we have done is considered capable of executing on the problems that we have at hand. And so when you look at the types of things that we end up doing in the industry, a lot of it looks like research. But the problem is when you look at this problem, you know what a new employee said to me one day at Fetch? They said, instead of trying to write a new mapping stack, we should just go buy a better laser. And they suggested buying an $8,000 laser that would solve this problem. And I agree, it might have solved the problem because it had a lot of range. But the problem is that LiDAR costs more than our entire robot. So that's not a solution. And those are the types of problems that we have. And so when you look at the problems that we're looking at trade-offs in performance. Typically, we are constrained by battery, not by compute. Who cares about compute when you only have 1.4 kilowatts of battery? That's it. Then you have to go charge. So you can throw the GPU and the machine learning and blah 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 neural nets. But if you can't run on a CPU, who cares? And I'm not trying to be lackadaisical here or controversial. I'm just saying that these are realities. And there's also the other problem is that you have safety critical processes. They need priority. You can't hog all the compute. You have then left over your limited resources for doing perception. And you end up using a lot more 2D than you would expect. We've probably spent the last 15 years looking at 3D and being like, yes, we have all the data. The problem is we don't have all the battery. And so we're left with, we have all these fancy things, but we really can't use them because the customers won't pay for it and they don't make sense in the environments that we operate in. So what do you do with all this? I mean, what can be done with all this limited information? And the fact is traditional methods, sometimes they fail us as well. Like if you look at methods like ICP, at your closest point. The problem is they end up leaving us with problems like this. I'm looking for robots. But the problem is a lot of times it thinks it's found robots, but it actually finds a trash can. And that matters because trash cans don't suddenly start moving, but robots do. But the fact of the matter is in an industry, when all your robots look like trash cans, cheat. We put retroreflectors on the robots. Bam, solved. Because we're able to then simplify our modeling very quickly. And so instead of using, something like convolutional neural net, we just make a simple kernel that looks like that, and bam, you have robots. And now you know the difference between a trash can and a robot. But these are things that, in general, would not be considered the realm of research. They would be considered the realm of engineering. And it's at times frustrating because we don't allow for the scope of the possible in terms of our acceptance of novelty and things like that, because we look at these things as cheating, as not solutions to the problem, but solutions around the problem. But this is a solution to the problem, and you know what the reliability on this is? 100%. Doesn't get much better than that. And why do we care about problems like this? Because one of the other problems that we have failed to address in research is this problem of sole agent syndrome. So most of what we do today in robotics is, from the robot's point of view, in almost a static world with basically defining the world as myself, free space, or hostile. And the problem is that this is not what reality is, and it ends up creating things like this. You know, this is a person's point of view. I have a pallet, I have a conveyor, I have a coworker, I have a boss, I have a forklift. But the problem is that the way our robots behave end up making people feel really crappy around the robots and not convinced to work with them, and then they don't want to work with them. And this is one of the finer points and nuances about the last decade and a half of mobile robotics research. We built a whole bunch of robots that can get from point A to B, but no one likes the way they do it. They don't. They hate it. In fact, they think robots are annoying and irritating, and they want them out of their lives in some cases. And so where do you start in solving this problem? And so if you look at what we've done at Fetch, we actually started engineering into the product and looking at use cases for how we deal with social behaviors with robots. And I'm going to use this to highlight a couple of things, because this is kind of the gist of it. This actually addresses 3 or 4 actual problems in like research industry right now, which is robots working well with people, robots not getting distracted and hung up on interactions with people. They actually slow down when they do these interactions. It slows down replanning. It also makes them less safe because they're less predictable. If 50% of the time the robot is going to go left or right, the person doesn't know what to do. In fact, that's one of the bigger problems with probabilistic planning today, is that it's not deterministic enough for people. It isn't. We have social norms that we follow every day in our environments. We walk to the right or the left based on our nation of birth, and then we follow those social norms in the country that we exist in. And the robots should do those same things. And so one of the things that we did is we started looking at what are the desired behaviors, and then what does the actual naive implementation do, right, for getting from point A to point B. And so this also comes true when you want to look at robots following. Robots have a tendency, because they're sole agents, to try and overtake. They're like, aha, I will try and pass that thing. But people don't like that. They don't like the robot creepily, hanging out behind them, trying to walk next to them. It's creepy to them. They don't like it. And so how do you handle some of these things? And so we started building into the navigation stack a whole bunch of capabilities for right biasing, a whole bunch of capabilities for dealing with less efficient routes and choosing the alternative route, which is the left. How to deal with unexpected obstacles. One of the things that you'll see is that robots will tend to basically, because they have this sole agent and they also have kind of a static world assumption, they will navigate around things that have already moved on. And it's kind of weird. People are like, why is the robot doing that? Not there anymore. But that's how our navigation stacks work. It will also do weird speed limiting things based on proximity, based on not understanding the direction and semantic view of the world. Like, that is a person, most likely will walk straight. It's not going to walk in front of me. Other things like following a person. This is one of the things that we still are working on in terms of cleaning up, in terms of trying to follow a person, not do this creepy thing. But I think one of the things that is really interesting is that when we looked at the simulation results to start, so this was about 9.5 months of research for us. And when you think about it, it's 7 full-time engineers for a period of 9 months. That's a lot of money. We care about this problem so much that we dumped a ton of money into this problem because it matters to the customer. We actually decreased the time to resolution in many cases by a large amount. And we also decreased the standard deviation, which was our measure of predictability for people. And you may say, well, who cares about simulation? And we really don't. We just use this as a baseline, because the next thing we did is we actually took So one of the things about Fetch is all the data that the robots have operationally is uploaded to the cloud. And so we have years of data of robots working operationally in warehouses. And we ran this robot behavior in these warehouses, and we compared it between, the 6 months before we deployed the software and the 6 months after. And so if you look at it in this customer site, they were already having low frequency interactions with people. The robots increased their velocity overall by about 8%. And the way we kind of look at low frequency interactions is also they had a relatively high path conformance. So the robots would traverse the same paths over and over again, and they wouldn't have to deviate very much because they continued to have low frequency interactions with people and other objects in the facility. But the things that's super interesting is when you look at high frequency interactions. So we have a customer where they're interacting with robots quite frequently, doing a picking behavior. We actually found that we were able to increase the velocity of the robots by 51% by doing social behaviors. This is a big thing. Like this is backed up by hundreds of hours of data, guys. And this is something that is in itself amazing that we're able to do. The robots that we have driven something like 10 million miles in 100 customers or hundreds of customer sites in 26 different countries today. And we're gathering all of that data. And we're leveraging it to basically do these types of improvements. One of the things is after we saw that the robots were getting these increases in velocity by time to resolve and to deal with these path conformance issues and high frequency interactions, we then went back and we actually increased the speed of the platform by another 45%. We actually increased the top velocity limit of the platform because we felt confident enough that the robots could resolve these interactions safely. And so I wanted to give you a peek inside of things that we care about and the problems that we're trying to solve and the data at which we're solving them. So I think one of the things that I would challenge everyone in this room with regards to research is you guys don't have enough data. You just don't. Like you guys are operating on 3 data sets. We're operating on 7 years worth of robotics data captured across hundreds of customer sites. And I know that it's not possible to do that by yourself, but I would encourage all of you to try and partner with companies to see if you can get access to their data to do research on. Because that's one of the things that's going to make it easier for us to transition your valuable research out of research and into the industry. And so with that, thank you, and let me know if you have any questions.
If you have any questions for Melonee, feel free to use the microphone in the hallway.
I'm curious about, so you talk about solutions like putting reflectors and robots to tell each other that they're a robot, but what happens when you get into environments you have like multiple robots from different companies that don't necessarily agree, or you leave a constrained environment like a warehouse and you're now working in like public space, like there's a food delivery robots and autonomous vehicles.
Yeah. So in terms of multi-robot coordination, we're just not there yet in terms of the reality of where we are in this adoption cycle. I mean, we have yet to operate a facility with other robots. However, there are companies starting to do it, and honestly, a lot of companies are willing to kind of collaborate and use these things. In addition to reflectors, we also use Bluetooth cooperation, so the robots actually emit like their forward predicted path and a bunch of other things. But still, there's no standards around that yet, and so it's still very ad hoc because we're trying to get alignment and agreement with the industry. In terms of going out into like the service robot space and the world, I would say we are struggling to operate in those spaces. Typically, they're highly curated spaces like restaurants, or they're highly unusable, or they end up in situations like they go for a dive in a fountain. And you guys know what I'm talking about, but these are the challenges that we're still dealing with. I don't think that we have good solutions for them yet, And I think that with the adoption, with the engineering time, because the thing that is killing us in the adoption curve is just reliability and stability of the mathematics solving this problem, right? Probabilistic robotics, however awesome it is, it comes with massive downsides because we're trying to use a probabilistic solution for a product that needs determinism. And that is one of the challenges that we have as a community.
Other questions? I actually had a question.
Yeah.
I also work at a warehouse-based startup. And working at that, like the customers don't like to share their data. Like they don't want their data to go offsite. But I fully agree with your point of like we need to share this data with academia so they can actually try on 1,000,000 square foot warehouses, not on 10,000 square foot warehouses. So do you have a strategy for convincing customers that sharing their data with researchers is a good idea? Particularly customers that don't normally work with academics.
Yeah, well, in general, this comes down to contract negotiation. I mean, Fetch very early on kind of made it clear to customers that the robot generated data is owned by Fetch. And so our ability to use that data with researchers is improved. But I think one of the challenges for your company is you have a lot of PII tied up in your data, and it's something we don't because we basically strip out any RGB images and things like that. And I know that your company does use RGB images. And so one of the things that you could look at is making a carve out in your contracts that make allowance for non-RGB, non-PII data. But these are all like, this is the realm of contract negotiation, not science, unfortunately. Although you could claim there is some science in that negotiation.
Any other questions for Melonee? All right, let's thank our speaker again.